The aim of this project was to utilize machine learning to lower the amount of pollution formation in jet engines.
Year after year, we emit tons of pollutant gases that cause the deterioration of the planet's environment and of the health of those living in it. Those emissions come from everywhere: energy generation, agriculture, manufacturing, and actually 28% of those come from the transportation sector. In order to address this concern, we studied aircraft engines. They work by allowing the air to flow through the inlet, through the compressor, and reach the combustion chamber, which is the cylindrical part between the rotating vanes that you can see in the video. That's where the fuel mixes with the air and then is ignited. This process generates a lot of energy, but also generates a lot of greenhouse gases, which are exhausted to the atmosphere.
Aircraft are the least efficient mode of transportation in terms of emissions per passenger for a given distance, so it has become increasingly important to find new concepts to reduce aircraft emissions. We started by training a neural network on a NASA dataset to predict how harmful the total emissions of an aircraft will be on both human and environmental health. It uses a database mortality index that we designed to assess the cumulative effect of the emissions as a single variable. We encountered issues with training the neural network because our dataset was not large enough. We hope to alleviate this in the future by using data augmentation methods to increase the number of data points. We are excited to continue learning and implementing the tenets of data science to help us solve this pressing environmental issue.
The general combustor design is shown on the right. The dimensions are carefully calculated to ensure that the air flows through the combustor as shown in the figure on the left. The complete annular flame tube is shown on the left. This was reduced to a 5-degree cutout to allow for CFD analysis and was modified to be an effusion liner to promote better performance.
Combustion chamber designed, it was now time to design the swirler and injector assembly to allow the air and fuel to mix thoroughly. Calculations for the hub diameter, core length, and other parameters of the swirler were made before designing it in CAD. Its assembly with the injector can be seen on the right. The injector has two tangential inlet orifices, one of which is visible right here, which control the fuel mass flow rate, and the exit orifice at the bottom was designed to control the fuel's exit cone angle.
In order to analyze our combustor, we explored the use of CFD in gas turbine combustion simulations. We learned the basics of the topic, including governing equations, computational domain, boundary conditions, meshing, discretization, numerical solution, and post-processing. As a result, we gained awareness of the complexity of CFD and will continue our efforts to properly use this powerful tool. In the future, we will assess the performance and emissions of our combustor and generate data for machine learning design optimization.
Throughout our study, we found that the residence time and temperature greatly influence emissions. With that in mind, we'll be developing a process of using CFD simulations and different combustor CAD models to obtain data on their emissions. And we will train a neural network to relate the design characteristics of the combustor to their emissions. That way, we'll be able to save months of design process to get to a more efficient combustor.
Now moving on to an instability analysis, we wrote a classification scheme that models a instability and tries to suppress it by varying just one parameter, and we use the fuel flow rate. These charts show the classifier's ability to detect and suppress a combustion instability. An ROC curve and a confusion matrix are the outputs of our code.
In the beginning of the project, many of our team members did not have a strong foundation in these areas of thermodynamics, fluid mechanics, heat transfer, CFD, machine learning, and combustion. But throughout the program, we were able to develop our understanding of these areas and apply these concepts to combustor design problems. We felt that our advisor had a strong plan and helped us learn according to our self-interests and to develop soft skills by presenting and submitting technical reports each week. We also felt that the program could benefit from a slightly longer time duration. We are excited to continue studying combustor design in the future thanks to this summer project and Professor Husty's support.
This work is submitted for the completion of Project R028, Smart Combustion Concepts for Low Emissions.
This concludes the video presentation for Team R028, Smart Combustion Concepts for Low Emissions. We would like to extend our sincerest thanks to the Purdue ME department and to the summer project sponsors for allowing us to learn about these innovative concepts for the past 2 months. So thank you once again.